So by knowing a parent graph and knowing something about translations, it opens up being able to graph almost every linear, quadratic, linear absolute value, or exponential, or even just a generic, what we call a piecewise function that we'll take a look at here, where it's just, there's no category for it. But if we have a starting parent graph and we know some other things about it, we can shift that around or translate it. So just here's a couple things. So assuming a is positive here, if you have a function and you add a number a to it, that will move your graph up however many units. If you subtract a, it will move it down. Okay. If you plug in x plus a instead of plugging in x, it moves it, it shifts it left to right, and in this case, it's going to shift it left. And if you plug in x minus a, it's going to shift it to the right. And we're going to start to see that on some of these examples. So here we have this first row, a series of parent graphs. Okay, so we have some kind of piecewise function. We don't even have the equation. We just call it f of x. We have a line, 3x, a parabola, 3x squared, now linear absolute value, 3 times the absolute value of x, and then your exponential equation, 3 to the x. And we're going to go through some of these translations. So this first one, if this is f of x, I want to figure out, well, what's f of x plus 3? So what's that plus 3 going to do to this original parent graph? Move it up 3. So if we know some key points, we could take those key points, move them up 3 units, and we get our new graph. So that's what we're going to do. And as a reference, there are some graphs on here, but those are just copies of the parent graph. So this is not f of x plus 3. This would be f of x right here. And so it's just make it easy for you. You can see, well, okay, if I want to draw f of x plus 3, I'm going to take each of these points, move them up 3 units. If this is 3x, what would how would we move it or translate it to find 3x minus 4? Go down 4. Okay. Here's our quadratic, and this equation was y equals 3 times x squared. That's the original. But what's happened now, instead of just an x, we're plugging in that plus 3 inside parentheses. So it's not tagged on at the end of the equation. It's actually just adding 3 to the x value. And so that's going to move it, kind of fits in with these right here. Is it left or right? It's going to move it left. So we're going to move left 3 units. Okay. And you may remember from Math 2 Honors, Vertex Form. It's kind of written in that way. And you say, okay, the vertex is going to, you do the opposite of what's here. You say it's at -3, and there's nothing here, 0. You see that. That's where your vertex is at -3, 0. This is your absolute value function. And again, the parent graph was y equals 3 times the absolute value of x. But now we want to graph y equals 3 times the absolute value of x minus 4. So what does that minus 4 do to the parent graph? To the right. And then our exponential function, we have a couple things happening here. So the original was y equals 3 to the power of x. And that's what's graphed here. Okay, that's what you see above. And here we have a minus 5 and a minus 2 to think about here. Now that minus 2 is part of the exponent, and if it helps you, you can always put that exponent in parentheses, because it is by, it's implied. We don't usually write the parentheses, but it's implied. And it may help you remember, okay, so this 2 is going to either move me left or right, and that 5 is that tagged on at the end, it's going to move me up or down. So I have to do two things. Move which way? Right 2, down 5. So from each key point, you're going to right 2, down 5. But remember this function has that horizontal asymptote. And if you move that right or left, it's still the same line. That doesn't change. But if you move it up or down, it's gonna be in a different location. And so we also have to move that down 5 units as well. What would the equation of this horizontal asymptote be? Y equals -5. Good. All right. So knowing these translations now opens you up to all kinds of graphs, and they can, and those numbers imply things if you know what the parent graph looks like. So I want you to try the same thing on the next row. So again, you have your parent graph, and you can, if you forget what the equation was, you can look at the top row and graph these 5 equations. could be. Thank you. Mm-hmm. This is exponential is the only one that has that line. Oh. Yeah. And there's like no way you could go like underneath it? No, it's stuck. Yeah, so it's called a horizontal asymptote, and it never goes beneath it. It just gets closer and closer to it. Yeah. All right, so should look something like this. First one, you're moving to the right 2 units. Second one, you're moving up 1 unit. Third one, you're moving right 5 up 2. The linear absolute value, you're moving left 4 down 1. And the exponential, you're moving left 5. And when you move it left 5, the horizontal asymptote stays put. Lines go on forever, left to right. And so if you move it left a little bit, it's the same line still. Okay. What I do want you to take note of is the number I'm highlighting here has nothing to do with the translation at all, right? That 3, actually it's 3 for all of them, has to do with the parent graph. In the first one, it's the slope of the line, right? In this one, it has to do with the width of that parabola. The 3 determines some part of that width. This one is the slope, again, of the right side of the V shape. Here, this 3 determines just how quickly we're increasing exponentially. Okay. So our goal is to come up with these equations and use some of these ideas of translations to help us graph quicker. And so we're going to do that. So as you go through these graphs, there's kind of a set of questions you want to ask yourself. And the first thing you want to be able to do is identify what's the general shape that I'm working with. And there's 4 options for you. Is it a line? Is it a parabola? Is it a V shape? Or is that exponential shape? And so on this first one, which shape is it? It's going to be a line. And we know that because we have just a y and an x. There's no x squared. There's no absolute value sign, and that x is not part of the exponent. So we know this is linear. Okay. If it's linear, I want to know the slope. What's our slope? -2. And I think of slope as a fraction. So we're going to drop down 2, go right 1. But before we could even use that slope, we need a point. And so then you want to ask, how is the parent graph point translated? So we said every parent graph of a line goes through what point? 0, 0. But there's a translation happening here. And what's our translation? Left 3, down 1. So our parent graph point, 0, 0, has moved left 3 and down 1. So it's no longer there. It's been translated. Where is it now? -3, -1. Okay, so you start with your translated parent graph point. And that gives us a point we can use here. So -3. And because it's a line, then you could use the slope to find, once you have a point, you can find the rest of your points. So you could drop down 2, right 1, drop down 2, right 1. Got 3 points I'm working with. Got my graph. Okay, so you always have that idea. So what shape am I working with? And then once you know what shape you're working with, there's maybe a little different strategy. Like if this is a parabola, I wouldn't be working with the slope. Okay, but I knew it was a line. And then how is the parent graph point translated? So on the second one, what shape is this going to make? The U shape, because it's quadratic, it's got that squared right there, indicates the shape. And then you think, okay, what's the parent graph point for the parabola? 0, 0. And then you think, well, how has it been translated? 0, 0 moved which way? Right, 4 units. So that's my first point. And then when you have a parabola, you know there's symmetry around this line. This is your vertex, is what you really pointed. And so you don't have to graph this, but there's an axis of symmetry that goes right through that vertex, which tells you if you find a point to one side of that, you got automatically a matching point on the other side. And so after you get that vertex, you're just going to pick an x value to the right or to the left of it. It doesn't matter. Stay close to it. If you go too far away, you're going to get something off the chart because they grow pretty quickly. So stay close to that vertex. I'll pick 2. So I'll just go 2 to the left and then plug it in and see what you end up getting. So if I plug that in, I'm going to get 2 minus 4 squared, negative 2 squared, which is 4. So 2, 4. And then because of the symmetry, I know it's going to match on the other side at 6, 4. It works that way with the exponential as well. And I kind of gave it away. So we have that exponential graph. And the exponential, there's 2 things that come with that. There's the point, which is at what? 0, 1 this time. And then there's that the floor or the horizontal asymptote. Okay, so those 2 pieces you got to keep in mind with your translation. Where are they? And so here, what's our translation? So that plus 2, that's in parentheses there. That's moving us left 2, and then that plus 1 moves us up 1. And the parent graph point was not 0, 0. Here's where sometimes it gets a little confusing, because if you use 0, 0, you're going to end up at the wrong spot. So 0, 1 was our starting point. Move left 2, up 1. So if you start at 0, 1 and move left 2, up 1, you're going to end up at negative 2, 2. Okay. And that's not the only thing that's been moved, but our x-axis, our horizontal asymptote, has been moved left 2, up 1. And so that's ending up right here at y equals 1. And then we want to get a couple other points. Now, exponentials, they're growing, and they grow pretty quickly. So if you pick anything to the left, you're going to get a fraction, because it's going to be between somewhere in between the 2 and the 1. So those are harder to graph. But if you pick stuff to the right, you're going to get integer values. If you go, again, too far to the right, it's going to be way off the chart. So you want to go 1 to the right, 2 to the right. Sometimes is even off the chart because they go pretty fast. But definitely go 1 to the right and try 2 to the right as well. So 1 to the right would be at negative 1. if we plug that in, we're going to get 3 to the power of negative 1 plus 2 plus 1. And you follow your order of operations, parentheses, do the exponent, and then addition. And what does that come out to be? 4. Negative 1, 4. And if we try one more, we plug in a 0 and get 3 to the 0 plus 2 plus 1. What's that going to give us? 10. That's going to be off the chart. So don't worry about graphing that one. Just sketch it. It actually should increase a little bit quicker than mine because it crosses the the y-axis at 10. So we do need to talk about domain and range, but let's do the graphing part first. So we're almost all paired up. We got an odd number here, but so whoever you're sitting next to, I want you to decide one of you is going to be a 1, one's going to be a 2. So decide that right now. You two pair up. You two pair up. I'll pair up with you. Okay. So decide who's a 1, who's a 2. Okay. And we're going to work on this one here. Okay. The one in the middle, the absolute value one. And if you're a 1, I want you to put your pencil down. You can't write. If you're a 2, you can't talk, and you can't really think too much. You're just going to do what the number 1 tells you to do, but you're going to be you're going to be the one working through this. So the number 1s are going to tell number 2s what to do. Okay, so go and do that, please. All right, so you're going to be number 1. I'll be number 2. Danielle, right? Danielle. Okay.
So are we dropping first? Is that what we're doing first? Or is it getting to the point?
Whatever you want to do.
Okay. I like getting the first point down first. So it's absolute value. And this is positive 4. It should be at 0, 4, right? Maybe. I don't know.
What do you want me to write? Whatever you want.
Put a point at 0, 4.
0, 4.
Okay. That's there. And plug in values first. So the first point was still on the parent graph. X is 0 and Y is 4.
Good.
I don't think 1 would be fun to do.
Just get practice.
Yeah, I don't like that. Work. 3 for the next point. So that would be, and then the next one, 6, right? For Y, it's 3. 2/3 times 3. 4 plus 3. 6. That's 3, 6. And I'm kind of lazy, so go to the same point. On the other side of it being negative.
That's not lazy, that's smart.
And write that point down. So that's negative 3. 6. Okay.
And
Draw the lines. Yeah.
Very good. And another way to do that is to realize this is a slope.
That works as well.
So after you got the first one, you can go up to right 3.
Oh, yeah. yeah. Okay. Yeah.
Lazy way, right?
Yeah. Okay.
All right. So, you guys get something like that? Okay. So, no matter what, you want to find this point first somehow, right? You recognize it's got absolute value, so you get that V shape. The parent graph goes through 0, 0, but this has been translated. That +4 is telling us move up 4 units, and that's a good way to get your first point. To get your other points, well, you know there's symmetry, and so if you got one side, you got the other. But it's also created by lines, so you don't have to do it like the parabola where you try to find another point. You can use the idea of a slope. The slope is up 2, right 3. I go up 2, right 3, got to that point. It's a quick way to do it. It doesn't work with parabolas, but it does work with this. This uses lines. And then you automatically got the third point. So you can get through that pretty quickly. Okay. This one, f of x equals 3 is a special case. What does it look like? Straight line. How's it? All lines are straight. But I know, what do you, the horizontal line, okay. Going through height of 3. Okay. That's your y equals 3. And no matter what, y is stuck at 3. And you pick whatever x value you want, right? What shape is this one going to be? Linear. But we need to change the way things look, because in this form you cannot determine translations. It has to be in function form. So you have to solve for y before you can decide any of that other stuff. And so solving for y, I'm going to subtract x from both sides. So I get negative 4y is equal to negative x plus 20. And then I'm going to divide all three pieces by negative 4. And I get y is equal to 1/4 x minus 5. So when I divided by negative 4, it was negative 1 divided by negative 4 gave me positive 1/4. Positive 20 divided by negative 4 gave me negative 5. So now it's in a form that we can work with. It's linear, so that means it's got a slope of 1/4 and a y. It is a y-intercept, but let's think translation. This is telling us to move our parent graph down 5. Okay, so our parent graph point, so down 5 from our parent graph point at 0, 0. That's our starting point. And once you have your starting point, use your slope. Up 1, right 4. Down 1, left 4. Okay. So you guys have some background with domain and range, right? You've heard of that a little bit? Okay. If you have a picture in front of you, you have a graph. When you're thinking domain, you're looking at it, well, how far left will it go? Not even how far left is it on my picture, but those arrows mean it's going to keep on continuing. Like this one is going to keep continuing to the left and up. This arrow is going to keep continuing to the right and down. So what's the furthest it's going to go to the left? What's the furthest it's going to go to the right? Okay, that's the idea. So for a line, what's the furthest it's going to go to the left? Negative infinity. So I mean, just negative infinity means it keeps going to the left, it'll never stop. What's the furthest it goes to the right? Positive infinity. And so there's a couple ways to write the domain, and there's a couple different notations. One is interval notation, and it looks like this. So negative infinity to positive infinity. And probably a new notation for you, but it's a notation we're going to use. Range, you're asking the same question, but you're asking, well, what's the lowest it will go? I didn't lose that much time, did I? Probably off. Let's see. It's only 140. We're done at 145. Got some time. Okay. So what's the highest it will go? So lowest is negative infinity, highest is positive infinity. So negative infinity to positive infinity. Okay. Let's just work with this notation. I'll bring in the other notation later. So let's try it on the next thing. For the parabola, what's the furthest left it will go? What's it? Negative infinity. What's the furthest right? Positive infinity. I'm seeing people come out of class. But our schedule, well, what do you guys want to do? Hold on. Let's see what they say.
Kalina Rodriguez,
Guess we're done.
Stephanie Chida, please report.
All right, we'll stop there. We'll pick up where we left off. So for homework, do what's on there, but domain and range you don't have to do because I haven't really taught that. But do the graphing part, okay?